Electronic spectra. Introduction. It has been discussed in the last chapter that when molecules absorb energy in the microwave region, far infrared region, transition between the rotational levels takes place, giving rotational spectra. Similarly, if the energy is absorbed in the near infrared region, transition takes place between the vibrational levels accompanied by those in the rotational levels, giving vibrational rotational spectrum. However, if the light is absorbed in the visible region or ultraviolet region, electronic transition takes place giving electronic spectra. A number of other processes also takes place on absorption of light called photoprocesses. These may be photophysical processes such as fluorescence and phosphorescence or photophysical reactions. The branch of science dealing with such process is known as photochemistry. In the present chapter, we shall take up a brief study of electronic spectra, whereas photochemistry will be discussed in the last chapter. Electronic transitions and band spectra. Theory of electronic band spectra. Just as there are electronic energy levels in an atom, there are electronic energy levels in a molecule also. However, there are no simple formula available for the energies of these electronic levels except for the hydrogen-like atoms. Electronic spectra are obtained when the electrons in a molecule are excited from a lower electronic energy level to a higher level. However, as the electronic transition is accompanied by vibrational and rotational transitions, the total energy of the molecule in any state is sum of the electronic energy, vibrational energy, and rotational energy. If EE, EV, and ER represent the electronic energy, vibrational energy, and rotational energy respectively of the molecule in the initial state before transition, and EE dash, EV dash, and ER dash the corresponding values in the final state after transition. Then we have energy of the molecule in the initial state E is equal to EE plus EV plus ER. Energy of the molecule in final state E is equal to EE dash, EV dash plus ER dash. Therefore, energy change involved in the electronic transition will be given by delta E is equal to E dash minus E is equal to delta EE plus delta EV plus delta ER. But according to Planck's quantum theory, delta E is equal to h mu is equal to hc mu bar. hc mu bar is equal to delta EE plus delta EV plus delta ER. Mu bar is equal to delta EE plus delta EV plus delta ER divided by hc. As for a particular electronic transitions, so that delta E remains constant, and for a particular vibrational transition, so that delta EV remains constant, delta ER can have different values due to different rotational transitions within the same vibrational energy change of the same electronic energy level. A number of closely spaced lines are obtained. This constitutes a band. For each vibrational transitions, separate band will be obtained. Thus, due to different vibrational transitions for a particular electronic transitions, a set of bands is obtained called the band group or band system. Each electronic transitions will give a band system and hence the complete electronic spectra involving different electronic transitions give rise to a series of band groups. Thus, the electronic band spectrum obtained for a gaseous molecule is quite complex. In spite of the complex nature of the electronic band spectra, these are preferred over the other types because these are obtained in the visible and ultraviolet regions so that these can be easily photographed and studied. Calculation of dissociation energy of molecules. A study of the electronic band spectrum reveals that at one end of the spectrum, the distance of separation between the lines becomes smaller and smaller till ultimately the line spectrum vanishes and space of continuous emission starts. The frequency corresponding to the point where the line spectrum vanishes is the frequency necessary for dissociation of the molecule into atoms. Thus, electronic band spectrum can be used not only for getting the information as given by the vibrational rotational spectra, but it can also be used in evaluating the dissociation energies of the molecule. Potential energy curves and Frank-Condon principle. The explanation of electronic band spectrum and dissociation energy can be early understood in terms of potential energy curve and Frank-Condon principle as follows. The potential energy curve of a diatomic molecule is obtained by plotting the potential energy of the system versus internuclear distance between the two approaching atoms. The curve obtained is of the shape as shown in figure. However, even at the minimum energy equilibrium position represented by point x, the atoms are vibrating so that the internuclear distance keeps on changing. Therefore, the potential energy keeps on oscillating about the minimum position. The vibrational levels thus occupied by the system may be represented by horizontal lines and indicated by appropriate vibrational quantum numbers. If sufficient energy is supplied so that system occupies the vibrational levels represented by Vd, the corresponding internuclear distance should become infinity. That is, the molecule should dissociate into atoms. However, this usually does not happen because before this stage is reached, the electron jumps to the higher energy level, that is, electronic transition takes place, and the dissociation will take place only of the molecule in the higher energy level. Now, every electronic state has its own potential energy curve. Two such curves for the lower electronic states are shown in figure by 1 and 2 respectively. They differ in the fact that the minimum of the potential curve for the excited state 2 is at a larger internuclear distance than at the ground electronic state 1. The dissociation energies for the two states are different as shown in figure, that is, d2 is less than d1. This is evidently due to the fact that the bonding in the excited state is weaker than in the ground state. The vertical distance between the minima of the two curves gives the difference between the electronic energy of the two states. The transition between the two electronic states takes place according to the Franck-Condon principle explained below. According to this principle, nuclei being much more massive than electrons, an electronic transition takes place much more faster than the nuclei can oscillate to change their internuclear distance. An electronic transition takes place from an extreme end of a vibrational level, example from A or A dash as shown in figure, because the velocity or vibrational energy of the atoms is zero at these positions and they spend maximum time at these points. As internuclear separation remains the same, the transition can be represented by a vertical line, example from point A dash to a point C of the upper curve, and not from potential energy minimum of lower curve to that of the upper curve. The new vibrational level must be one which is nearest to point C. Counting levels, it appears that the excited molecule will be in the third or fourth vibrational levels of state 2. This explains why in the electronic transition there is no simple selection rule for the transition among the vibrational levels. All types of transition from lowest vibrational level to any of the vibrational level of higher electronic state are possible. It may be mentioned here that according to quantum mechanics, the transition from the lowest energy level takes place from the midpoint of the vibrational level, which is the equilibrium or the most probable position, and not from the extreme positions. Each vibrational level has a large number of very closely spaced rotational levels which have not been shown in the diagram. Now, when the transition takes place from vibrational level of the lower electronic state to some vibrational level of the upper electronic state, it is accompanied by a number of transitions between the rotational levels. The result is a group of closely spaced lines called a band. Since a number of vibrational transition takes place, a group of bands called the band system is obtained. Further, as the transition takes place between many different electronic states, the result is electronic band spectrum consisting of several band systems. If electronic transition similar to A-C takes place, the result is an absorption spectrum consisting of a number of vibrational bands. If, however, a transition similar to BD takes place where point D represents the vibrational level corresponding to which the internuclear distance is infinity, the molecule dissociate. Thus, when such a transition takes place, the absorption spectrum consists of a number of bands corresponding to transition from the ground state to definite vibrational levels in the upper state. But these bands will converge and finally pass into a continuous region or continuum which has no fine structure. The point at which the continuum starts is called the convergence limit, the frequency, and hence the energy corresponding to this limit gives the dissociation energy of the molecule. However, it is important to note that after dissociation, atoms are produced in the electronically excited state and not in the ground state. Hence, to obtain the energy of dissociation into ground state atoms, the excitation energy of the atoms must be subtracted. Lastly, it may be pointed out that if the minimum of the electronic state is nearly at the same internuclear distances as that of the ground electronic state, the transition from mu is equal to 0 of the ground state to mu is equal to 0 of the upper state, that is 0-0 transition, is the strongest. Electronic spectrum of a diatomic molecule. As shown in figure, in case of diatomic molecule, when a photon is absorbed by the molecule, the most probable electronic transition takes place according to Frank-Condon principle is from mu is equal to 0 of the lower electronic state to mu is equal to 2 of the higher electronic state. This is called 0 to 2 transition. Other transition from mu is equal to 0 level of the ground electronic state to different vibrational levels of the excited electronic states also takes place, but with much lower probabilities. Thus, the transition from 0 to 2 has the maximum intensity, whereas other transitions have smaller intensities. The result is a spectrum of the type shown in figure. Selection rules for electronic transition in molecules. In order to understand selection rules for electronic transition in molecules, we should first understand a few terms and symbols to be used therein. First one, parity. Parity represents the behavior of an orbital with respect to inversion. It is used for molecular orbitals of homonuclear diatomic molecules. We consider a point in the molecular orbital and note the sign of the orbital. Then we travel equal distance through the center of the molecule to a point, center of inversion, on the other side. This operation is called inversion. If at this point the orbital has the same sign, it is said to have even parity and is denoted by G from Gered, German word for even. If the orbital has opposite sign, then it is said to have odd parity and is denoted by U for ungered, uneven. The parity designations apply only to homonuclear diatomic molecules because heteronuclear diatomic molecules like HCl do not have center of inversion. As shown in figure, a bonding sigma orbital has even parity and is written as sigma Z. A sigma star orbital has odd parity and is written as sigma U. A bonding pi orbital has odd parity and is denoted as pi U, and a pi star orbital has even parity and is denoted by pi Z. Multiplicity of state. The ground or excited electronic state of any species may have one or more unpaired electrons with the spin in the same direction or opposite direction. If S represents total spin quantum number, then 2s plus 1 gives the spin multiplicity of the state. If S is equal to 0, multiplicity of state is equal to 1. It is called singlet state. If S is equal to 1 by 2, multiplicity is equal to 2. It is doublet state. If S is equal to 1, multiplicity is equal to 3, it is called triplet state, and so on. For example, in the ground state, S2 positive has only one electron, its multiplicity is equal to 2. Similarly, O2 molecule in the ground state has two unpaired electrons with parallel spins, its multiplicity is equal to 3. Term symbols of molecules. These symbols give complete information about the state of the molecule, that is orbital angular momentum, multiplicity and parity. Depending upon the component of the total angular momentum about internuclear axis, they are given the symbol summation, pi, delta, etc. as shown. Component of the total orbital angular momentum about internuclear axis and their symbol. To the above symbols, multiplicity is added on the left as a subscript and parity is added as a subscript on the right. For example, the single electron in S2 positive in sigma molecular orbital has zero orbital angular momentum, hence the term symbol is summation. Further, it has multiplicity is equal to 2 and then parity of the only occupied orbital is G star. Therefore, full term symbol is 2 summation G. The term symbol for any closed shell homonuclear diatomic molecule is 1 summation g because the spin is 0. As all the electrons are paired, there is no orbital angular momentum from a closed shell and the overall parity is z. If there is only one pi electron outside a closed shell, its orbital angular momentum about the internuclear axis is equal to 1 unit, hence the term symbol is pi. If there are two pi electrons as in O2, the term symbol may be summation or pi. The term symbol mu will be used if the electrons are orbiting in opposite direction, and which can be so if they occupy different orbitals. The term symbol will be used if the two pi electrons are orbiting in the same direction, which can be so if they occupy the same pi orbital. In case of oxygen, in the ground state, the two pi electrons occupy different orbitals with parallel spin, and the overall parity of the molecule is equal to closed shell into G is equal to Z, and the term symbol is 3 mu G. Lastly, a subscript plus or minus on a summation term symbol is added to show the behavior of the molecular wave functions or reflection in a plane containing the nuclei. In case of O2, one electron is in 2 pi x, which changes sign on reflection in the yz plane, and the other is in 2 pi y, which does not. The overall reflection symmetry is therefore closed shell into plus into minus is equal to minus. Hence the full term symbol is 3 summation negative z. However, we give below the selection rule for transition between different states of the molecule. Only those transitions are allowed between the states for which the difference in the component of the orbital angular momentum along the z-axis is equal to 0 plus minus 1. Thus, summation minus summation, pi minus summation, delta minus pi transitions are allowed, but delta minus E is not allowed. The transitions are allowed only between the states having same multiplicity. The singlet and triplet transition may occur, but triplet transitions are forbidden. Summation pi minus summation plus and summation minus transitions are allowed, but summation plus summation minus are not allowed. Only those transitions are allowed which are accompanied by a change in parity. Thus, ZU and UZ is allowed, but ZZ and UU transitions are forbidden. This is known as Laporte selection rule. Molecular orbitals sigma, pi, n involved in electronic transitions. The most common molecular orbitals present in a molecule are the bonding molecular orbitals sigma and pi, and the corresponding anti-bonding molecular orbitals are sigma star and pi star. Besides these, there may be heteroatoms such as nitrogen or oxygen present in the molecule which have orbitals containing lone pair of electrons. As they are non-bonding orbitals, they are designated as n-orbitals. They do not have any corresponding anti-bonding orbitals. In case of homonuclear diatomic molecules such as H2N2 etc., the highest occupied molecular orbital HOMO in the ground state is a bonding molecular orbital BMO, whereas the lowest unoccupied molecular orbital LUMO is an anti-bonding molecular orbital ABMO. The electronic transition takes place from HOMO to LUMO on absorption of suitable energy, usually the total wavelength part of the ultraviolet region. The transition may take place from n orbital to the anti-bonding molecular orbital. In other words, the electrons may be excited from sigma, pi or n orbital to sigma star, pi star orbitals. Thus, the transitions which are allowed are sigma to sigma star, pi to pi star, and n to pi star or n to sigma star. Read as sigma to sigma star, pi to pi star, and n to sigma star transition. The type of transition involved depend upon the nature of the compound and takes place by absorption of frequencies characteristics of the compound or the group present. Taking the example of carbonyl compounds, aldehyde and ketones, the sigma, pi and n orbitals and their excited state are shown in figure. Thus, the transition taking place are n to pi star at lambda is equal to 280 nanometer and pi to pi star at lambda is equal to 180 nanometer. Further, it is interesting to point out that if a single electron excited from the lower orbital to the excited anti-bonding molecular orbital has a spin opposite to that of the electron left in the lower orbital, The total spin of the excited state is S is equal to 0, so that multiplicity is equal to 2s plus 1 is equal to 1. Hence the excited molecule will be given in the singlet state. If the two electrons in the upper and lower orbitals have parallel spins, S is equal to half plus half is equal to 1, so that 2s plus 1 is equal to 3, that is, the excited state is triplet. Thus excited states are classified as singlet or triplet. The triplet state has lower energy than the singlet state in accordance with Hund's rule. As already explained, Otto in the ground state is in the triplet state. It shows an exceptional behavior as the electronic transition takes place from triplet ground state to triplet excited state instead of singlet excited state. That is why the spectrum of Otto molecule is quite complex. The type of transition which certain categories of compounds undergo and the reason or the wavelength absorbed for these transitions are given below. Saturated hydrocarbons or compounds containing carbon-carbon and carbon-hydrogen single covalent bond requires very large energy to produce electronic transition, usually beyond 116 nanometer. In such molecules, sigma to sigma star transitions takes place. A simple olefin has an absorption band at about 170 nanometer. In such molecules, pi to pi star transition takes place. Molecules like methylamine and methyl iodide which do not contain pi orbital undergo N to sigma star transition. All electronic transition in organic compound do not occur in the ultraviolet region. The occurrence of colored compound indicates absorption of radiation in the visible region. The compounds containing nitrogen-nitrogen double bond group or long conjugated system of double and single bonds including aromatic ring absorb at a wavelength greater than 180 nanometer. That is why they look colored. Such groups are called chromophores. In such cases, the energies of the molecular orbitals lie close together and pi to pi star transition takes place. Example, the protein beta carotene has a fairly long conjugated system and shows absorption at about 240 to 280 nanometer. Intensity of electronic bands. The intensity of any electronic band depends upon the extent of overlap between the wave function of the ground state and the excited state. Greater the overlap, greater is the intensity. As there is a very poor overlap of the wave function in the N to pi star transitions and there is excellent overlap in the pi to pi star transitions, the intensity of the band produced by N to pi star transition is very low as compared to that produced by pi to pi star transitions. Further, in the presence of an acid, the electrons of the N orbital undergo protonation and the N to pi star band disappears.